Okay. I see what you're saying. Okay, cool. Yeah, so excited to be here to be presenting this one paper called Objects as Points by Zhou et al. You can go to the next slide, please. Yeah, so kind of the overview that I'll be presenting this paper is first beginning with like the background and also like the motivation, and then going into detail the ML model that was described in this paper called like the CenterNet model. I'll go through some of the key components of this model, and then if we have time, I'll just kind of go through like a brief code like walkthrough. So in these slides, there is a link to a Google Colab notebook where anyone can play with this open source. It is like this code base that I created that is a re-implementation of this model, but it reduces a lot of the complexity that was it was implemented in the authors so in the original work, but has all the key kind of components implemented with the goal that anyone who really wants to dive deep into both the math and the code that is completely open source and easy to run. And then the last part of this presentation, I'll be going over just a few of like the lessons that I've learned trying to implement this architecture from scratch, and also like some limitations of like the model and kind of what's next on the horizon. Yeah. Oh, can you go to the next slide, please? Thanks. But yeah, but a brief overview of me. I'm Andrew Mendez. I'm currently a deep learning solution engineer at Hewlett Packard Enterprise. But I think like the main kind of takeaway is this like paper is close to my heart, and also like my background, since I've over the years being in the ML industry space, I've been doing like a lot of things like with object detection and also computer vision. So yeah, so if anyone has any like hard challenging questions, there is not a thing as like as a dumb question, so feel free to interrupt me and ask like questions. I really do enjoy like an interactive chat and yeah, talk. If you can go to the next slide. So yeah, so kind of going into like the background. So for anyone in the audience who either has some experience with either ML, computer vision, or if you don't have experience, so kind of a key thing about this paper is it's implementing an object detection model. And so the simplest way that I can describe what object detection is right, with ML, like there's a lot of different architectures and like tasks. And so one subset of AI and ML and also deep learning is the ability to analyze objects and content within an image. And so object detection is within the realm of image processing and also computer vision, where pretty much these ML models, so it takes in an input of an RGB image, and so what the model will do is it will predict kind of like object detection. So pretty much it will one, help to localize where all the objects are within the image and what is like the class ID, or like kind of what is like the object. And so if you see on like the image, so kind of right, so there's also image classification and object detection, just kind of like, but the key kind of difference, right, is that for image like classification, it's going to give a prediction of what is the most prominent object within the image, but not providing any more information, which is not the most informative if your image has a lot of objects within the image. But with object detection, it will not only but describe, okay, like there is a car in the image, but where is this car at? And as we'll see, there's many different ways object detection architectures and like researchers have encoded object detection like labels. So I'll go more into that. Can you go to the next slide, please? Yeah, so the key kind of takeaway here is that an object detection model given an input image will predict the location, which we'll see like as 4 numbers, and then like the class of the object, which is just a single number.
Can I ask a question?
Yes.
So having never worked in this domain before,
yeah.
Is there an advantage or disadvantage to using these different bounding box formats? Because I know that there's some
yeah, totally. So that's a good question. I think it's I think keeping up with object detection, like research and how it's bled into the not bled, but how it's blended into like with the industry. A lot of these different formats came from design decisions that authors of lots of different object detection models. I think for sure some of these formats were very crucial for certain object detection architectures that use those labels. So for example, like with Cocoa format, well, actually specifically, so you see on the slide, like YOLO v5, I think regressing the center location, I think, is easier for and I guess like for like an optimization like problem. But they also did like a lot of tricks where they use a lot of prior information. So it's yes and no. Like I think if you pair the label format or how you represent the object based on the architecture, and we'll actually kind of see that, you can you're able like to use I guess assumed information to help kind of predict objects in the image.
There's no more data in one or the other of it. Like it's just right?
So yeah, and I think the one thing I wanted to call out, and you'll see like in like the next slide, is that it's so important when you're working with object detection like architectures to be aware of what is the object detection format, because I've personally gotten tripped up where I'm working with, for example, when I work with a YOLO v5 model, which is a open source version of this object detection model, they use this format, but I think that it's used, or I assume that it's using a completely like different format, and so that trips me up. And then if you know, so with being able to get ML to work, you need to make sure that like all of your labels are correct, that all of the code that's using to preprocess and train is all aligned. So I think just being aware that there's these different formats will save a lot of headache. So yeah, if you go to the next slide. Yeah, so kind of going more into like these different object detection like formats. So yeah, so at least with the image on the top, right? So kind of like here is an image with a cat. And so you can kind of see, like, you can see that these 4 points are not like encoded as what we're used to, right? Like in math, like with Cartesian coordinates, but it's like in pixel space where the origin is like at the top left, and then the end location of the image is in like the bottom right. There was a lot of reasons. I think there's like a lot of historical things that were in like that resulted in the images being in this format, but that's out of the scope of this presentation. I won't go into it, but just to help to see, okay, like how within like this pixel space are objects encoded. And then as you see, you know, we see like the Pascal VOC, like the Pascal VOC like label format, and then with implementations, also like with Cocoa format. I think the key kind of takeaway here is that these different object detection label formats can vary really differently. And as you see, like with implementations, some of these labels are also like normalized. So it's really important to really make sure that based off of the architecture or some open source code base that you're using, that you understand what is like the label format, because it has tripped me up a lot. But just to kind of help to set like the background, if you go to the next slide. Yeah, so kind of pretty much the key kind of takeaway here is that there's many different ways to represent an object in an image, and that's just been due to how like researchers wanted to like define it. They kind of pair the, I guess with like the label format to really like they would encode it in like a special format to kind of help the optimization problem. So I think like a lot of object detection architectures would want to normalize it because it's easier to optimize a model where, right, like you have your predict labels between like 0 and 1 versus like from 0 to 640 by 480. So yeah, it's just be aware. That's pretty much the main like takeaway. If you go to the next slide. Yeah, so then, okay, so now understanding how objects are represented in an image, now going through the historical or kind of like the background of what has been done in object detection like research and like industry up to 2019. So I'll first begin. So within object detection like research, there's two like different architectures of models. You have two-stage object detection networks, and then well, so it can also be called single stage or like one stage. Sorry. Object detection network. So beginning with two-stage. So when deep learning was really hot and up and coming in 2015, a lot of like deep learning based object detection like models were built in like this two-stage like format. So really like with the first stage and comprised of like this feature extractor that you see all of like the gray blocks, and then this proposal like generator stage. And then for like the second stage, you have the detection like generator. So pretty much for like the first stage, like the main kind of takeaway is, so for object detection, it's very tricky to get high precision of detecting an object within like an image. So what really helped at that time was, okay, so we're going to extract like features using, you know, kind of what was like the state-of-the-art image like classification models. But then to kind of ease the optimization learning of like of the training process. So let's first have the model propose a lot like of candidate object or object detection like regions that either have an object or it's just background. So they're not directly predicting what is the class label at the proposal like generator stage. Pretty much what they're doing is they're kind of really trying to have like, but the highest like recall like possible. Like, okay, like here are 2,000 object detection like regions that have a high chance of there is an object. We don't know what that object is yet, but let's just propose as many like candidates as possible. And then so kind of with these extracted features and then all of these candidate object detection regions. So now going into like the second stage, we're going to align image features. We're gonna like do like some warping and like some shearing. So pretty much we're aligning all of these features extracted into like these candidate like regions to then kind of like have this good like alignment. And so this one layer is called the ROI, which is like the region like of interest. So, but just kind of like the key like takeaways that like there's some alignment that needs to be done, and then kind of there's just like a series of CNN like layers to then get that precise like bounding box location, and the classification label. So that's like two-stage object detection models. Yeah, so like if anyone has any questions on that. But then kind of also kind of quickly going like in like to one stage, around 2017, there's a lot of complexity with two-stage object detection kind of framework. So for every each of like these sub like networks, especially like in two like stages, you have a completely different set like hyper parameters that you have to tune, and those hyper parameters change with like with new data sets. And so kind of as of 2017, there was kind of this push more like for one stage where let's just kind of do this all like in one like forward pass where we kind of extract good like features from like the input image and then directly regress both kind of the object detection like labels like and like classification. So and then I just so like I'll pause here for any like questions or anything that's kind of unclear or confusing. Yeah, go ahead.
Basic question. What does blue mean versus gray?
Yeah, so I guess in this diagram, so for the feature extraction stage, at this time, a lot of state-of-the-art feature extraction like networks, they were based off of large image like classification like models. So I think the representation here is to show that each of those gray blocks, that's the extracted features at that certain stage. So let's say this input image is 512 by 512, that gray block is the first, so that's the features extracted from the first stage of the network, which is, let's say it extracts like 120 features where the output is 256 by 256. There's always going to be this reduction in like resolution for each gray block. And then that blue block is kind of like that blue box is, I believe, trying to represent, okay, this is the final size of the set of features that have been like extracted from all the previous layers.
So is it that the gray blocks are convolution and pooling, and then the blue blocks
yes.
are NLP?
Or I think the blue box is just the final pooling of that layer. I guess there could be flattening. I think a lot of object detection models want to keep like that spatial to like that 2D representation, so that because for object detection, what's unique for other image like processing problems is that you want to know like where like the like object is, and at that point you're gonna get like high confidences in some regions and then not. So if you flatten it, you're going to lose that signal, if that kind of makes sense. Any other questions? If not,
I just have another clarification.
Yeah.
Because it just seems like the labels are an important part of like pre-processing the data. So I just want to clarify. So some of the labels are normalized, some are not normalized.
Yeah.
Do some of the computer vision models require normalized versus not normalized weights? So then in certain situations, you need to know the model, or is it like model agnostic? So it doesn't matter what model you're using.
That's a good question. I think
based on your experience.
Yeah, I think the best way to answer it is, so some object detection models. So if you look at like this RetNet like model, I'm trying to think. So each object detection architecture that was proposed by different like authors, when they release their open source like code base, like there's a lot of design decisions that were done. So I think from what I've seen, when like you normalize your labels, that makes it easier. Like so that helps with like the training process because it's generally harder to regress numbers that are not like normalized. So there's that component of it. But what's interesting is in this architecture that sort of I'm but describing, we actually don't do like that normalization when we want to regress the width height. So these models are capable of regressing, if it's not like normalized. But one architecture that comes into mind specifically, it's called like the YOLO architecture. So you only look once. They explicitly like do this normalization, and you also see that with I also mentioned like with you also like YOLO v5. They also do like that normalization. So I guess I guess in summary, it's like the Wild Wild West. I think people do different things. It does help, but you can alleviate that if you train your network right. So yeah, it's definitely like a convoluted answer. So it's kind of what was done with that architecture and kind of with that code base.
There's an XKCD comic about that. It's unreasonable that there are 4 standards for this problem. We should come up with a unified solution that everyone can use.
Yeah.
A year later, it's unreasonable that there are 5 standards for this problem.
Yeah.
The 3 post problem.
Yeah, it's definitely, but it's always good to like ask these questions for each object detection architecture that you're going to play with or you're going to train on a new data set, because there's so many bugs or things that can break your model that if you're not like attentive of, and exactly where like I think I've dealt with where I was like, okay, I created like this data set. I'm going to retrain this architecture from this code base with the new data set, and it doesn't learn. It's because they assume that you need to normalize it, but they didn't explicitly say that. So yeah.
The strict subset for the detection generation will only ever generate either it'll either completely discard one of the areas of interest that were generated by the proposal generator, or it will crop it. It'll never choose something that's not part of that.
So your question is, sorry, like, could you just repeat it actually?
So the detection generator does a strict, what the results of the detection generator are a strict subset of the proposal generator. So it will either reject one of the regions that are or use most of the regions in the proposal generator.
Yeah.
Or choose a subset of one of them, or a cropped version of one of them. We'll never choose anything outside of it.
Yeah. So for the 2-stage, I believe that that all of like the candidate regions are proposed at that stage, and then the detection like generation kind of stage like does like some filtering, but then also some tweaking of like the bounding boxes. So at the proposal like generation stage, they're usually bigger than than what the actual object is, but then with how like the second stage is but designed, it will like fine tune that. But I don't believe that new object proposal like candidates will be like generated at the second stage. Like pretty much what was like generated at the first stage is all the possible, which that's why it's so important to make sure that you tune your hyperparameters right for that first stage. Because one example is, so a lot of like the data set, or one like benchmark like data set that is used to like to train and also like to benchmark these models are objects from like Flickr. But I kind of have the experience of trying to adapt this architecture to objects and satellite like kind of imagery. And if there's more objects than what your proposal generator can generate, it's going to miss objects. And if you don't, so like it's one of those things too, yes, that you need to make sure that your proposal like kind of generator is going to really maximize like the I guess like the recall or all like the possible, or like the amount like possible objects that can be in your image, else you'll miss it. Yeah,
Question?
For sure.
So if you don't want to answer this, and
That's
you
okay.
want to move on to something that doesn't say background on the slide, totally valid too.
Yeah.
But I've been thinking about the different bounding box formats. Would it be a true statement, or would
Oh, so like some more information to help to represent the object.
Well, it seems like, with X1, when you're doing raw coordinates, distribution would be somewhat evenly spread through the image with maybe a little bit more weight towards the middle, across the data set, whereas with listen, you would, I would expect you'd have like a fairly tight Gaussian, around, the average bounding box size. So in my head, when you're detecting similar sized objects, so with type 1 would do better, but when you're detecting like arbitrary sized objects,
Yeah.
you could feel things.
So I think that's interesting you brought up that question, because one thing that I wanted to talk about, but I almost forgot, so this really helped, is that both of these architectures, so in like the research like literature up to this point, both for 2-stage and like for 1-stage, a key component of these architectures that is not in this diagram is and I believe in the proposal generation stage for 2-stage object with detectors, but also in the detection generation stage for like 1-stage, researchers encode like priors within like, so they encode priors call like anchor boxes. So pretty much they encode what are the likely 5 sizes of like objects that we'll see in so what is like the distribution of like sizes that we would see in this data set. And so that kind of helps also both with the proposal like generation and also like with filtering, that is that early in the training stages, I guess for like 2 stages, they'll just directly encode it. So the proposal kind of generation, so let's say like the largest size of an object should be 500 by 500 pixels. It shouldn't be higher than that. It's not even going like to generate that. And for, I guess like for 1-stage where you can't explicitly encode that information, adding that prior will help. And that's what a lot of these architectures and all like a lot like research have done, but then it's just another set of hyper parameters that you need to account for if you're going to tune it onto like a new like data set. I think so a lot of the priors that are encoded within like these off-the-shelf object detection models are actually very like generalizable. So you don't like, it's a very subtle thing people don't think about, but but these like researchers and these object detection like networks do encode priors that you can explicitly state. But it's one of those things that if you're going to apply it to a new like data set, such as objects and satellite kind of imagery that don't fall within that distribution, it's going to be like a missed, or it's going to miss those like size of objects, and it's going to miss those objects, if that kind of makes sense. But yeah, I think just the last point, I believe they don't really encode specific, they only encode object detection sizes and kind of like also like the aspect ratios. So like some objects are have more width than height, some have height and width. So that does help with the kind of learning like and the final performance of the model.
Then putting through like clipping or ReLU type stuff, or is it through loss function?
That's a good question. I think it's just a hard-coded hyperparameter. I think that is a good research opportunity to how can you encode that in the learning process. But I think that's one of the things that that definitely makes me realize, I think like a limitation I need to better understand, like, is that proposal like generation stage, because there are some networks that like there's some parameters that are learned, but there's some that are fixed. Yeah, it's like definitely like a lot, but it's fun though, because like when it works, it's awesome. Like, it's cool. So if you can go to the next slide. Okay, so as we described in a long-winded way, right? So we have 2 like stage versus like single stage. We described what like the both like the limitations of like all of like these hyper parameters that you have to account for, especially like with all the priors to of the anchor boxes, which is just like the distribution of object sizes, also the proposal like generation stage. So kind of given just like, I guess, a lot of things that are being considered within object detection architectures. The authors from Zhou et al., kind of really went for this like problem of let's like simplify object detection without like losing performance. If you go to the next slide. And so the way they did this was, okay, let's like represent objects as center points or really like as key points. And this was at the time, like no one really, or I think there was some kind of research that was done where someone actually proposed, okay, let's use two key points to represent like an object. It's the top left corner and the bottom right. But I think what was really cool about this kind of paper was like, let's just compute the center points and let's use that as like a representation. And so at that time, there was a lot of great kind of research done in key point estimation, where there was a lot of great both research and architectures and like loss functions that show that you can train objects really well to like, if you have like a labeled like data set of, I'm going to use key points to label semantic objects, or so given like a label like data set, that this key point encodes a semantic part of the object or the image. So you see on the bottom right, you see these blue kind of key points. So you see you're encoding like the wrist, the elbow, and the eyes. So there's a lot of great kind of research that shows you can get these deep neural networks to learn key points that encode semantic features of objects. And so they kind of, but the researchers of Zhou et al. Kind of took it to the extreme. Okay, let's try and get these kind of models to learn semantic features that can eventually regress to just like only like a center point. And there was a lot of benefits that came out of this. Pretty much, this kind of made it easy to sort of continue the research realm of single stage object detection. But they also kind of realized you can encode a lot of information about an object using like this key point or like using like the center point. And so the authors also used this key point center point representation to encode the width height. And they also adapted this to 3D object detection, where you can encode how far, like what is like the distance of the object to the camera, what is the object's orientation, including like the location. So I think that the key kind of takeaway is if you have enough data and you kind of have a reasonably good architecture, I think you need a really good loss function and good diverse data. Like these models can learn a lot of things that if you try to do hard encode with traditional ML techniques would be very hard. But pretty much, so a lot of these innovations, being able to represent the object as like a center point, and like not using any anchor prior like this distribution that's hard coded, like let's learn it through data. And yeah, so it kind of just really, all of this resulted in like a lot of like simplification, that is, I guess in theory, like much more kind of manageable than like having these two-stage object detection, having separate proposal generation architectures, and including the anchor boxes or kind of the prior distribution. Yeah.
To make sure I understand, is the difference between this and like the COCO data format, I think, so the one that was centered and then was that this architecture first looks for semantic key points like left elbow, right elbow, and then draws a bounding box around that. And then finds the center of mass of that, right? Yeah,
so pretty much, so how the labels are encoded. So we saw one format, which was like the YOLO V5, where you have the center X, center Y, and then the width height. So like that's the same encoding kind of format that is done with like CenterNet. But what's unique about CenterNet is they actually they do some processing to encode the model, that I think makes it easier how do I describe it? So they basically encode it again, like before the model like does its forward pass and learn. I guess in like more of like a spatial format. I think I'll have to show you to like see it, but I guess what's tripping me up or not is that so there's other kind of models that use this label format, but the difference between CenterNet and these other models is other models have directly regressed, like like this four-dimensional, I guess like tensor, where it's like the center locations and then the width height, but CenterNet will actually like, yeah, it just learns in like a different way that I guess helps with like the simplicity of it. If yeah, so but I'll go more into detail into that kind of. Cool. Yeah, so I guess like one kind of limitation that has been improved on since like 2019 is I think one challenge to acknowledge is that if if two objects are very close to each other, like the center points are going to collide. And so new kind of research since like 2019 has helped like alleviate this. And even new like single stage architectures, but to kind of help with this challenge. But this is one like limitation of this like paper. Yeah. Yes, kind of just going like the key kind of takeaway here is that being able to represent objects as like a single point actually, helps make this object like implementing and training object detection models simpler. And, like they show that they kind of reach state of the art performance. I think in some cases better than what was the state of the art at the time without like loss of performance. Let's go to the next slide.
So I just have a
Yeah.
clarification.
Yeah.
If I'm right or wrong.
Mhm.
So it just sounds like CenterNet, this using a point to represent an object.
Yeah.
Is you're just able to encode more information spatially than just like the bounding boxes. You're also able to encode, right, like you were saying.
Yeah.
Other features of the, like, so like in a regression model, it's not just like the bounding boxes, it's also
Yes.
certain, it goes above and beyond that. Is what you're saying.
So
Is that?
yeah, I guess like that's a really good question. So I think what the authors are arguing is that I wish I can show this. I think I'd better show it like in like the Google Colab like notebook, but um can you actually go back a slide? Go back one more. Keep going right here. So I think one thing to highlight about this, right? So other object detection models would learn to directly regress the four numbers of a bounding box. And so with like CenterNet, I don't think I explained this that well. If you look at the second kind of screen, so you take an object detection label and you're directly creating a different like representation that is kind of so yeah. So if the input kind of image, right, like is 512 by 512, the actual output is a two-dimensional array that is like the same like spatial like 2D sized or close to it. And that helps. I think what the researchers argue is that helps to encode a lot of spatial features that or a lot of these spatial features that the model has to learn to ignore other areas of the image and have to learn very strong features that in this area of the image, this is where the eyes are. So as you see this, and I think another point that I didn't highlight was that how we're encoding these center points, it's not just a single point, it's actually like a Gaussian like 2D like distribution. And so I think that helps to kind of encode it like spatially. Sorry, this is kind of confusing.
Hierarchy part of that one of my examples, you have people and within
Right.
each person has different points.
Yes. Yeah.
Is that part of the CenterNet data? Is that like hierarchy of the people and within the people there are points, or is that just for demonstration for visualization purposes?
Yeah, that's a good question.
It kind of looks like in the model diagram, key point, heat map. Is that what they're showing?
Yes. Yeah. But you do see the lines, and so that does kind of beg the question, like, is there some kind of hierarchical representation that's either encoded in the data or learned? There isn't for a lot of these models, which is pretty surprising. If you have a labeled like kind of data set that you kind of label all these key points and you're consistent, but you also have a lot of diverse examples of people, right? Like some are farther than others, different orientations. the model will learn with enough diverse data that pretty much like this key point corresponds to eyes, this key point corresponds to elbows. And I think that's definitely like there's a lot of research now in the AI world about how to have models like interpretable and like robust, because there really isn't a good explanation of how does it learn this. It's just magic, or it's just there is like the manifold hypothesis that like within the space of images there is nonlinear like manifold, that there's good features that lie within that, but it's pretty like black magic. But yeah, but yeah, I can keep going. Okay, so how much time? I think I've been going on.
7:15. 7:16.
How much more time you think? 30 minutes, 20 minutes?
Okay.
Okay, yeah, well, yeah.
In theory, 7:45.
Okay, perfect. Okay, yeah. So then I'll like definitely be sure to be done by 7:45 or earlier. Okay. So I think we've talked about a lot, and we've kind of we've kind of seen a lot already, but I kind of something like, because it's one thing to read a paper, and then it's like another thing to implement a paper. And I think like you learn a lot like from that process. So I think with this kind of diagram, what I wanted to show is how an input image gets processed, and then like how you would actually decode the predictions. So starting with this kind of input image, this is a synthetic like data set where let's say the input image like size is 512 by 512. And it's a 2-class like data set. So we encode, so it's a synthetic set of images that has circles and squares. And so we encode circles as class ID 0, and you have like the rectangle that's encoded in class 1. If you see on like the left hand side, and then kind of going back to the object detection like formats. So you first see this is the top left location, and then the width height. So it's in like the Cocoa format. Then we convert it to like the center X, the center Y, and then the width height. And so kind of what we've already like talked about. So we have this feature extraction layer. So we kind of have this 512, and then it passes through a series of layers where you're reducing like with a resolution, but the output of features that are extracted is very large. So let's say like 1024. So it results in a 3D array of 1024 by, let's say, 16 by 16. So it reduces the spatial resolution, but you've learned a lot of features along the way. Then you have a series of upsampling like layers, because we want to maintain that spatial resolution, but we need to kind of like increase it. So I think if you see in the top left, this architecture that I've kind of implemented, the output like resolution is 128 by 128. So it's definitely a smaller like resolution than the actual input image. But there's both engineering decisions for why we do this. And yeah, but at least, and then this is similar to how the author implemented it. I think a key point though is, so like a limitation, so setting the output like model size by 128 by like 128 2D like resolution. The most amount of objects you can detect is like 128 times 128. So if your data set requires more objects, if there's a lot of objects in this image, all you would have to do is just add another upsampling layer. So I think that really shows the simplicity of this model versus a 2-stage object detector. You would have to change like the hyper parameters for the a proposal generation stage. You may want to check that the distribution of like boxes sort of like is in line with what you already have. If not, you need to sort of like add that prior like sort of like change that distribution in the 2-stage. Here you can just upsample, but you need to have a large diverse like data set, so you're giving it examples that eventually really describe like the entire like the entire like distribution of objects and their sizes and whatnot. So so you have the feature extraction layer, you have the upsampling layers, and then there's 3 heads. So this is where you regress. So this key point heat map, you regress the center X and center Y. Then you regress but the size. So if you look at the key point, so it's a 3-dimensional array. So, but since this is a 2-class data set, so really there's only so it's 2 by 128 by 128. But depending on your data set, like that would change. But what's fixed is, this would output. So for the size like heat map, this is fixed because you're only encoding the width height and then like this offset. So this offset was proposed by the authors to alleviate the problem of their object detection architecture, because it didn't output at the same like resolution as like the kind of image. You're losing that you're going to lose like the resolution of the precise location of your object, but you can overcome that by actually encoding that kind of offset. So pretty much like that offset, if you want to learn more about it, like I kind of included some math, but pretty much your kind of object size is in the 512 by 520, that 512 space. When your model kind of output is at a reduced kind of resolution, like your object is also like the object, the dimensions and the location is reduced. And then so kind of to kind of get that precise like bounding box, they kind of just include this offset prediction. Yeah. So that's kind of, yeah. And if anyone has questions, I can go more into detail, but for the sake of time.
So what is exactly the offset heat map?
Yeah, so the offset heat map, I guess, yeah. So if you follow through, so how to decode the prediction. So, okay, so the ground truth is, let's say for the first object, 301 center X, 69 center Y. If you kind of divide that by 4, that's kind of at, right. So you see like 75.25. So around like, so when it's reduced to 128, like it's like a fraction. So it's not like integer. So, so pretty much like with integer truncation, you're going to lose that 0.25, but that's why you kind of, so you keep that offset of, so if you look at the CX, right? So 69 times 4 is 300. But you keep track of that ground truth is actually, sorry, I said 303, it should be 301. So that offset is 1. So pretty much at the inference stage, so you get the center point at that reduced like resolution, you're going to multiply by that scale, right, times 4, and then you're going to add that offset. And that helps to get you back that ground truth like resolution. Because if not, then we would need to sort of make sure that the output is at the same resolution as like the input image, if that kind of makes sense.
So the offset compensates.
Yes.
For the fact that the model reduces.
Yes.
The images.
Yep. Yeah. Cool. Trying to go to the next slide. Yeah. So the key kind of takeaway, this like diagram just really shows, right, like how the input image is going to be like processed throughout the network, and then how you would like decode to get close to or to like get to the model prediction that in the ideal setting like will be very close like to the ground truth. Okay. Keep going. Next slide. Okay. So if there's time, let's see what time it is.
20 minutes, pretty good.
Okay. Well, I probably won't go because I've already went through I've already went through like a lot of information, but I think just want to let the audience know. So this is an open source Google Colab notebook. That's kind of based off of this open source implementation that I've created that you can actually play with. You can actually play like with like this model architecture. So this will actually synthetically create an object detection like data set. It's just a 2-class data set if you want to scroll down. And then all of the core implementation of kind of like these key ideas. So here in this cell, we create this synthetic like data set. Keep scrolling down. A lot of good stuff in PyTorch. So, oh wait, if you can stop here. Yeah, so this was all implemented also like in PyTorch. So if you want to go into like nitty gritty of how this works, I think here I wanted to highlight. So back to, I think I didn't do a good job. So we have an encoding of how we encode the ground truth like labels. So it's actually in like a JSON like file. That's kind of like a software engineering like format. Oh wait, if you yeah. So the cocoa shapes dot like JSON. Oh no, but I would just like go back to that. But it's right here. But pretty much going back to, so I think CenterNet was basing their model off of research done in the key point estimation realm, where rather than like having having the network directly regress these four numbers, you're going to encode that center point into this 2D into like a 2D matrix. And so you see it's kind of hard. You kind of see this one circle. So pretty much I took this two like dimensional array. So for the first layer, that encodes all of the key points for class 0 within the image, and then when you index 1, that's like the second class. So you see that the ground, so kind of like the heat map. So this encodes this is where the center point is for the circle, and this is where the center point is for the rectangle.
Like 0 everywhere except where the actual
Exactly.
object is.
Right. Okay, if you want to zoom out and then keep scrolling. I just wanted to highlight that. But yeah, so pretty much there's like a lot of fun code to unpack in this notebook. So if you wanted to dive deeper, keep scrolling. I'll stop here. So this is just I just wanted to show that this is the code to actually render the center point in like a 2D into like a 2D like Gaussian like distribution. This is the code that was implemented by the author. There's probably other ways to implement it. And I've tried other kind of implementations. This is just one of like the better ones. And yeah, I just wanted to show how you encode the key points. If you keep scrolling, this is just more code on how to encode the kind of key points. If you keep scrolling down, so this was something that when I tried to implement from scratch, so this is the function that the author wrote to implement how to encode the object size so that the model can regress it. So they kind of did that same thing, right? We have this 2D array where everything is black, but where that center point is, they kind of encode the actual raw like resolution like of the object. So if that object was 50 by 50, it would be 50 by 50. It's not like normalized 0 to 1. That could be like a research question. Is it better to normalize it or not to normalize it? I actually tried it, and without it, I think I've seen a better performance just having the model directly regress the width height, not normalized. I just wanted to show this code because I tried to do it another way, and it didn't do a good job to learn to learn like the width height.
So another question,
yeah.
if you don't normalize it, is it generalizable to other data sets? Or is it only for the data set?
Yeah, so I think like how this model regresses, it will learn to generalize well from the data you give it. But that is a good question. Is it enough to generalize well to other data sets? I think the better way to describe it is it's probably taking it's right, like it's going to resist. So I think it's just making it more of a data like driven problem. So rather than to generalize it, have the model learn like that like distribution rather than having to hard encode it. So if you have a large like if you have a large like data set that encodes, it should learn that distribution maybe better than hard encoding it, but it really depends on you should just empirically just train it on that data set that you're interested in and see if it's going to generalize or not, if like that makes sense.
It can be frustrating.
Like the resolution, like basically it's gonna be a product of the resolution, right? It'll like, oh, looks fine on this data set, and then the other data set.
Right.
It is 512 by 512, not.
Right.
by 1K, and
Yeah.
it's all the size.
Yeah, and then that kind of brings up when it comes, so like other data sets, right? Like you have images in different aspect ratios and resolutions, and so there's other things that I've done to help like compensate for that. I won't go into that because it's just more engineering and technical, but yeah.
But the actual heat map itself is it's like a 2D, it's a 2D, it's like it would be like an RG.
Yes, or it's pretty much,
red, green.
I would best describe it as a black and white image where the same region that center point is located, it's directly putting in like two numbers, right? The width like and like the height, like unnormalized.
Yeah.
And I guess what's interesting is the model is still, I guess like the model can learn features because it's spatially there and it has to reason through all of this is nonsense. Like I guess it's one of those things like, does that help generalizing it more or better to regress? It's just what this architecture did, and it did well. And they're like, the researchers were all excited and we're like, oh, this is great. I think it makes it simpler to, it definitely makes it easier to represent like objects that may, I think, help the optimization problem, if that makes sense. If you want to keep scrolling. I think, keep going. Just the point I think that I really like about with this architecture, if you keep going, I just here's like the backbone of this model. So I'm taking an off the shelf model from PyTorch. You see up one, up two, up three. So that's like all of the upsampling kind of layers that I described in that slide. And then you have the two. So in the slide, the author, right, has three like heads, right? So you predict the key points, you predict the width, height, and the offset. Actually, for this demo, to make the model simpler, because I was curious, kind of like a research question, can you regress only the key point and like the width, height, and get good results? And it turns out that you can. So I think that's pretty interesting, but it's not like, it doesn't have the most precise, but it can, I think it does a good job. So I think that was a cool finding.
That base network, then the encoder part, and then the F1, F2, F3 are
Yes.
these encoder heads.
Yes, or so it's like that upsampling set of layers, and then the out C and out R, those are just the decoder heads, or like that's like the final output. If you keep scrolling down.
Oh, yeah.
I think to highlight, so what the authors I think did mention, but actually they leverage prior work from the key point research literature and even other object detection kind of literature. Just the thing I want to highlight is they do some initialization of the output heads to actually help with the optimization process. And I just wanted to call it out because this did help improve, or to help train the model to improve the performance further. Because if not, what PyTorch does, it'll do like this random initialization, which like doesn't really help. Okay.
So question for the
Yeah.
upsampling code,
Mhm.
just because I saw that it was 512, 256, and then 256, 256.
Yeah.
Why wasn't it 512, 512?
Oh,
And then
so
256, 256?
yeah.
And then the other thing is, if you want to upsample again,
Yeah.
what would your code look for, like if you're upsampling like a fourth one?
Yeah. So I guess like, so this actual implementation, I kind of defined it where the model, like, so the input size is 256 by 256. And there was some background kind of motivation. So in like another slide, we'll actually see. So I actually have this model. I have an example of this model like running real time, like on a smartphone, and to get that real time processing to work pretty quickly, having the model process at 256 is just, it's just less like floating point like operation. So, but I could redefine this architecture at 512. I just chose 256. And I don't know if this answers your question, but pretty much like, I think kind of one challenge is that like, it's important to make sure that your ground truth labels are either at the same like resolution as the model expects the input, but if not, you need to make sure your pre-processing code is right, because it'll cause potential more bugs and stuff. But yeah, it wouldn't be hard to like to keep it at 512, but I kept it at 256 for efficiency reasons, to have it train faster, and it can run pretty fast on mobile phones. But did I answer your question kind of, or?
It's okay, we can move on though, because
Okay.
we're running out of time.
Okay. Yeah, I think the rest of the code you can just play with on your own. It's just all like available here to kind of, so it just like, yeah, so if you actually scroll down, yeah, so this is like the loss function that is used to actually help the model learn to regress on like the center point, or not to regress, but to predict the center locations. I won't go into it because it would take me a long time to explain it. But this was a key thing that helped. But this is the point, is that this is just like the loss function that is used to predict the key points. And if you scroll down a little bit more, what is really nice, we just use a simple, I'll keep going down. We just use a simple regression loss to actually regress like with the width height. So I think that's just nice simplicity that is used to learn both like the key points, like, and the width height. Cool. Let's go back to the slide and then I'll finish up.
Can I ask a quick question?
Oh yeah, go ahead.
Are these heads then trained separately, or are they jointly trained with different?
They are jointly trained. And there's actually some good research that I think researchers have found that you get better performance if, because I think what researchers did study for this architecture is, so you have your upsampling layers, but then you have two separated upsamplings, and they actually show that if you joint train your key points and offsets, you're gonna learn better than,
Better feature representation?
yeah, a better like feature representation on like the localization part than if you kept all three, both the offset, with height, and the key point. But I think that gets into like nitty gritty, and I think like what I've learned is implementing this, but with a different architecture, like different style, like the model will learn. But you're right. I think like analyzing that, you can get further performance, but the model will learn with very simple like architecture, which is really nice. Okay, if you can, yeah, back to the slides. Cool. Click, yeah. Yes, presenter view. Yeah, so if you click this, I just wanted to show, kind of like to prove that that code works. So this is actual like the model. So I was running like real time on like an iPhone that predicts the location and also like the class IDs. This was a 7 class like data set of different fruits, and it was able to, and class 2 like was like orange. At least I believe so, but yeah. You can go to the next slide. Yeah, but yeah, I wanted to show that. I think like the power like of this architecture, it is, whoever says object detection is simple, it's always complicated. But yeah, and so kind of wanted to share some lessons learned. So I really challenged myself to wanted to implement this model from scratch. I was really excited about it, but I learned a lot, and I learned a lot of painful experience, but good experiences. So it took 10 plus months to implement this with 4 code like rewrites. And I learned, I think where all this headache has stemmed was I based my implementation like from a random notebook from Kaggle, which it got me to get something running, but there was a lot of bad engineering choices that if I would have studied the author's implementation, I would have had a much better or a smoother experience. Could go to the next slide. Yeah, and I thought that GIF was funny because people are saying that AI is going to take over the world, but my AI barely works, or it kind of does. Yeah, so pretty much just want to share some recommendations. Definitely start with a benchmark like code base. If you can, if you can get the author's code base to run, you're going to do really great, and even better, really study that original code base, because you'll learn a lot, like how should the loss function look, what is the ideal performance, save you a lot of headaches. If you go to the next slide. And then, yeah, I think for whatever model you want to re-implement from scratch, make sure you know what the GPU hardware requirements are. So for a lot of like image classifications, simpler models, you can run off of free like resources like Google Colab, object detection. The benchmark data set's very large and takes days to train. So just make sure you have efficient GPU kind of hardware to really benchmark and stress test your model. And that's it. Thank you for listening. I know it was a whirlwind. Yeah. Feel free to take a look at the open source code. Feel free to ask more questions or yeah. Thanks for your time.
Yeah, thanks so much, Duncan.
All of my detailed questions about bounding boxes.
No, I think about it a lot, and so it's nice to talk about it out loud.
Your friends don't want to just talk about bounding boxes.
I've usually complained about bounding blocks like different formats representations because it's definitely been like a headache both personally and professionally, but I think the more you suffer, like the more you're just aware of it. But now I can share that knowledge to other people. If you're doing if there's one takeaway, be aware of how the architecture, the code base, how they want your objects labeled, because if you don't get it right, it's not going to work and it's going to fail. You're going to cry. You're going to be like, why it's not working?
The equivalent of like row, column, like matrix order in
Right.
computer graphics. Like,
Yeah.
you will get it all the way around. There will be a point where it's just like, what if I just flip it? See if it works. Oh, it works. Okay.
What's the trouble with neural networks? I mean, you have to get top 10 before it shows you whether it works.
Absolutely.
So how long does it take to train one of these things on a non-trivial data set?
Yeah. So for that synthetic data set, I feel like I have a good succinct answer, but it all depends. But so for that synthetic like data set, it definitely doesn't take that long. And what's really surprising is the model learns pretty quickly. But I think it's interesting with synthetic data, or for that specific synthetic data set to learn where is this rectangle and where is the circle. It's actually, I guess, a very easy data set versus the benchmark data set, which is like the COCO data set. There's 1.2 million examples. So that takes, if you have a batch, so the batch size, you're training 16 images per training iteration. That could take you a few days, or I think I've had it takes 2 to 3 days. But I guess how quickly too, it can depend on if you set up like a distributed training. So if you're doing like single GPU training, it's going to take a long time. But if you have like 4 GPUs and you can use torch distributed, that really speeds it up. But it still takes, I think the fastest has been 15 hours, but it definitely, so it depends on the size of the data set and other factors.
Is it fine-tunable? Like if you were to take the COCO data set and
Yes.
say, I want to detect dolphins underwater.
Yes. Yeah. I think that's what's really impressive that I think allowed object detection to go from research to industry. So this is a personal like opinion. Object detection is one of the most like valuable computer vision models in the industry because it works like really, really well. And I think a key contributor to that is this benchmark data set has been used to pre-train a lot of object detection models. And I guess like with the distribution of objects, how diverse, like that data set has 80 classes. It just has really, it's a great pre-trained set of weights that then you can fine tune on a lot of data sets. But what's interesting, so where I worked previously at Clarify, if your data set's really big enough, you actually don't need to pre-train it, but it needs to be very big. Like that was in the order of magnitude of like 1 million images. So yeah, I think like these object detection models benchmark on that COCO data set, it's really good pre-trained. So then you can fine tune on your own data. But yeah, if you don't, it does. I think the one thing with this standard net model is it takes far longer to actually like generalize than I would think it would. But that could be an error in my code. That's why like after 10 months, I finally just read the author's implementation and I was like, okay, he can train a model on this harder data set in 26 epochs. It takes me 500. There's something wrong with my training code. But yeah.
That normalization might help with too, right?
Yeah.
keeping the width overall lower, so you have a lower L2 nonlinear.
Yeah, it could be that. I think so I made my life harder where the actual architecture is order of magnitude smaller because I wanted this to run like on a mobile phone in real time. And you definitely see a huge drop in performance by the number of parameters that are in the model. So like the author, I believe, the model that he trained was 15 million parameters, like a gigabyte or two in size, and that really does well in that data set. I tried it on mine, which is less than a million parameters, and it really struggles. So, but I think that
On the same data set?
yeah, like on the same data set. So, but it's interesting because there's this other model that I'm looking at that regresses just the four coordinates, like the center and the width height, so it doesn't do that 2D label encoding with the same amount of parameters that I try, which is less, which is it can run fast on mobile, and they actually get pretty good generalization. So it's like this paper, and I get excited that, oh, this is much simpler and it's going to generalize better. But then here's this other open source code that this one person wrote that, and it's generalizing better than what I'm doing. So it's, yeah, I feel like that neural networks are beasts to tame. They're,
The professor described it more as the biology than mathematics. There's math involved, but like,
or I think it's like you hit your head on the wall like hard enough and you'll find the problem or something. It's, yeah, it's definitely like a love-hate thing. But I think that's why having a really good baseline starting from the author's implementation, because you learn a lot more than if you try. I mean, it's good to try it on your own too, but I think doing both kind of really helps because, yeah.
So did you do it based on the author's implementation to get some more results?
So when I started, I didn't use the original author's implementation, but then my latest version, so not this example, but a different code base was based off of the author's implementation. And I actually, yeah, like do get a lot better results, but still not as good. But that's just, but once I use the author's original architecture, then I get good results. So
Same
that's
results you got?
similar, not almost the same, but similar.
But
Yeah.
how similar?
Less than, it's plus or minus 5%.
Okay, so not bad.
Yeah, it's not bad, but it'd be nice to get exactly. But I think there could be a lot of
Using
things.
the same code in the same data set.
I think I use my own training code, but I used their model.
Gotcha.
Or actually, and then I did the vice versa, where the model that's very efficient on mobile, I plugged in that to the author's code base, but the performance is a lot less. But that's probably because I guess the size of the model was not nearly as big as what the author did, and that is a key contributor to that.
Because you shrunk the images is what you're saying.
Or I shrunk the model, or like the model parameters. I think like, I feel like a lot of researchers chase for the state of the art, and they kind of allow themselves to make these really huge models and do a lot of things that don't really work in real settings. So I think like that's how they can achieve that performance. But there's great kind of research where like you have efficient models that are training, but at least like from my experience, yeah, it's you just need like bigger models will get you 95% of the way there. And then the little tricks, right, where you want like to do some normalization in your loss, or you're like clipping the loss, like these little training things can get you that rest 5% kind of thing.
Yeah, I guess my question was just more at like reproducibility of results. Like, can you reproduce these on like, because you're also using different hardware, this hardware like impact. I don't know, this is my area.
So I think
So that's why I was just asking,
for
like,
object,
did you do like re-implement the entire paper as he did it and get the same?
Yeah.
Which we don't have to talk about because like again, we're getting over.
No.
But I guess I just wonder like in terms of like how important reproducibility is to my scientific field and just whether or not
yeah.
your field has
So
achieved
reproducibility is important, but there's an ML reproducibility crisis that's going on where but it's been getting a lot better because a lot of it's open source, so you can reproduce it. I think like, right, like doing like rigorous kind of research, I think a lot of like researchers and PhD students, like they're going to start from like the author's implementation and then kind of take that to where they want to be. When I first started, I just wanted to learn how it works, get to the fundamentals. But then when I struggled with a lot of things, then I went to the actual author's implementation. But I think like even then it's like trying to get my code to look more like the code base. It would have been a lot easier if I would have started with the author's code base and kind of went backwards to how I wanted to, because there's a lot of things that I didn't account for that the author did that was very insightful.
In terms of this reproducibility, as it doesn't help with extending research, but did the author provide safe model files? Like checkpoints for.
So he did provide checkpoints, and he didn't explicitly state model size, but at least the checkpoints were like available to pretty much like at least, yeah. And it took a little bit of effort to get his code to run, but it's not like impossible to do. But I guess I was coming from the experience of like, oh, I'm just curious, I'm having fun. But then so when I got this like this simple model to work, and when I really wanted to benchmark it and really kind of make sure I'm getting good performance, that's where it was an uphill climb, because I was trying to get my code to look more like that when I should have just started from the kind of good implementation, because there's a lot of design decisions that were really key to getting that performance, such as model size. And
Now you know why those bad decisions were made.
Yep.
You know, because he
or then like I struggled, and then when I added what he did piece by piece, I was like, wow, like that you need to do that and do that and do that. So that's why I'm sharing to the world. Start with a benchmarked implementation from the author, ideally, because you're better off from dealing with a lot of headaches that I can imagine other people have dealt with, but for almost a year.
The other checkpoints, though, in terms of
Yeah.
scientific honesty, reproducibility, the author checkpoints got the metric or produced the metrics that they reported in there.
That's a good question. I think even in that repo, I think some people who ran the open source code were not. I think some were able to get the exact, some did not. I think maybe I don't think difference of GPU makes a difference, but I think for this repo, the author did a lot of really good work and support once he open sourced his research to help other researchers who were extending his research to like answer questions and write into kind of to get that. I think he did mention there's some things you need to do hardware wise or make sure you have with hardware so you can get that. Yeah. Thanks for your time and thanks for your patience. I know it was a lot. It was so. I think I'm gonna do easier projects from now on, but then again, it's fun when it gets to work and stuff.
Thank you so much.